Hello, and in this presentation, we will talk about default and training robust deep neural networks. So what are deep neural networks? A neural network is a batch of neurons that take inputs, do some math, which occurs in the hidden layer, and produce an output. Those hidden layers are extremely powerful, and by increasing the number of the hidden layers, we can get a deep neural network. So one of the functions of the deep neural networks is image classification. So a deep neural network is able to tell this an image of a whale which is correct. However, a problem occurs when there is slight change in the original image. At first, those three images shown looks the same. However, only the image on the left is the original image. The two images on the right are slightly different from the images on the left. For human, we are still easily able to identify this a whale. However, it's not so easy for a deep neural network. A perturbation, simply put, it is a mask that is applied on the images in order to deceive the deep neural network. So as shown in the example above, a whale with some noise overlay on it will produce an images that's only slightly different, but the deep neural network classify it as a turtle.
So you might be wondering, what is deepfool? Well, deepfool is a new algorithm that was created with the intention of producing perturbation masks, as we saw in the previous slide. Adding perturbed images to the training data can actually make the network much more robust. If you think about it, the whole point of a perturbed image is to try to misclassify it so that the network can learn to ignore these slight changes that can occur in images. Deepfool is special because the perturbation it produces are significantly smaller than similar perturbation creating algorithms, as well as potentially faster than them. Now, the paper used several different data sets and networks, and the specifics of them aren't nearly as important as the results. On the x-axis of these graphs are the number of epochs, and on the y-axis is the robustness of the network. The blue line represents a network trained with deepfool, the yellow line represents a network trained with fast gradient sine, and the orange line represents a network that uses neither. Interestingly enough, in these first two examples, you can see that the fast gradient sine actually produces networks that are less robust than had they never been used at all. The researchers hypothesize that this is because the perturbation created by fast gradient sine is significantly more than what's actually needed. And so the image falls outside of what would naturally be in testing. We'll end by showing off this table that charts the average testing error.